All right, so today we are looking at curve sketching, and curve sketching is nice. It'll tie together all the stuff we've talked about so far, except really the mean value theorem. Otherwise, the rest of it, increasing, decreasing, concavity, critical points, all that stuff, inflection points, comes up here. So if you don't have this part of your notes, that's fine, but this is basically an overview of what we're going to learn to do today, these first 4 steps. So what we need to add to our little list of tools is we have 4 cases that are going to help us work through curve sketching. The first one is if a graph is decreasing and concave up. So, yeah, pull up the claw. That's concave up. And if you're looking at it, which one is the decreasing part of it? Well, it's the one that's going down, right? So it would be this part of it, decreasing and concave up. It would be like that. I guess it depends which hand you were looking at. I don't. Yeah, some of you are arguing. Anyways, but it should look like this. Decreasing and concave up is this piece. And if we are increasing and concave up, that means we look like this. Decreasing and concave down is this piece. And increasing and concave down is this piece here. Okay, so that's about the only thing new that you need to be able to survive today's curve sketching, is that you have to be able to take what you learned from first derivative test and that, increasing, decreasing stuff, and add it to concavity. So you get 4 pieces now. So I'm going to walk you through this process here. So you're going to become a graphing calculator. Well, you'd probably rather just use a graphing calculator. It's not that cool, but anyways. Our process is the same. We're going to find a derivative. So start here at 6x squared plus 12x. And factor it, and I get 2 critical points here, x equals 0 and -2. So what I'm interested in is where things are increasing, decreasing. That'll tell me too about the extrema on this graph. So we'll do a quick number line, and it'll happen at 0 and at -2. And we're just going to pause here before we fill things in on the number line. You'll see why in just a minute, but it helps to go the rest of the way because we want to talk about them all together. So it'll make sense why I'm asking you to pause right now. Sorry, did I? Yeah. Just wanted to make sure you were paying attention. So the next thing that we would do, in this unit so far is find the second derivative. And that would be 12x plus 12. And of course, we're going to want to factor that into 12x plus 1. So I have a critical point at x equals -1. And that's the point that I'm going to be interested in looking at here for the concavity of the graph. But here's why I wanted to put them all together, is if all I did was pick a point in the middle, like say I picked the value, who knows, maybe I picked -1. That only tells me what's happening at one spot, and really, because -1 is one of my inflection points, I'm also interested in what's happening there as well. So you want all 3 spots on the number lines, because then I'll be able to tell you what's happening with the concave up and increasing, concave down and decreasing, whatever the combination is. So if I was to look at my pieces, I have x and x plus 2. Finding the positives and negatives is still the same. So everywhere to the left of 0, this one's negative. Everywhere to the right, it's positive. But it's those 4 regions that I want. And then for x plus 2, everywhere to the left is negative, but positive to the right. And this is the piece x plus 1. So everyone to the left of -1 would be a negative, and everywhere to the right would be a positive. So just like before, I'm interested in the overall effect. So the overall effect here is a positive. The overall effect here is a negative. The overall effect here is a negative. And the overall effect here is a positive. So notice that there's no change in some of these intervals because I added those extra spots. But the reason I want those extra spots is I can tell you exactly what's happening in this interval. This graph is increasing because it's positive first derivative, and it is concave down because it's decreasing. So without seeing the curve, I know that it has to look something like this, increasing and concave down. But if I didn't have all the intervals laid out like that, it would be harder for me to find them. That's why I'm putting them all in a combination this time. Okay, so the points that I'm going to look at to do this curve sketch, there's some easy ones. You know, it never hurts to have extra points. If I stick in x equals 0, I get a nice point at -3. It was easy to find, so I might as well include that. Had nothing to do with calculus, but gives me some extra information about this problem. I also have these points here. I'm interested in what happens at 0. Oh, sorry, it was there. I lied. Thought I was being smart. So we know that's -3. And then if I stick in -1, I'm going to have 2 times -1 cubed plus 6 times -1 squared minus 3. So it'll be -2 plus 6 minus 3. So that should be +1, I hope. So I've got another point here at -1, 1. And the last point see where we end up now. That'll be 2 times -8, so that'll be -16. And 6 times 4, so that's +24, minus 3. So I believe I have 5 here. So -2 and 5. Okay. So these are like the minimum amount of points that we want to focus on in this graph. They were my critical numbers and my inflection points, right? Or my possible inflection points. And what I'm going to do is walk across the graph trying to figure out what it looks like. So what happens here, I already mentioned, this is increasing and concave down. I'm looking at this whole vertical pair here. Okay? So increasing concave down, that's to get to the value -2. So it's got to look I don't know exactly what it's going to look like, but it's going to be something like this. It's got to be increasing and concave down, and then it hits that point. Then once it hits that point, what happens in the next interval? So the next one is this spot here. Can you describe it for me in 2 parts?
Decreasing, concave down.
Yeah, decreasing because it's negative here, and concave down because it's negative there. So it's going to be this part of the graph. Decreasing, concave down. And then we'll cut one more interval here. What's happening in that next one? Decreasing, concave up. So that'll look like this, going down, but it's now concave up. And then the last thing that's left over, everything larger than 0, what's happening there? Increasing and concave up. So the picture will look like this. So if I wanted to know what does this graph look like, roughly that's my sketch of the curve. Okay? If you need more detail, it means you have to start plugging in some extra points, but using concavity and increasing and decreasing, we can capture a lot of the way the curve is going to be in between those points. Okay. I guess I suppose it'd be a good thing just to compare it with the actual. Okay. So I guess some part of you, I mean, you've grown up, you're like, what do they call you guys, the wired generation or something like that? You know, you've never had you've never known what it's like not to have technology. Like, did any of you ever have to go turn the channel by hand? Yeah? Really? Wow. Okay. Yeah. You had an abacus. You know, not that old, but anyways, you have to appreciate that where curve sketching came from was back when they only had pen and paper to work on, and it was very handy back then too. Of course, this is much more convenient. Let's see though what we come up with. to have something that looks like the one I've given you, it goes from -4 to 4, to 2, and it goes +5 and -5. So I'll just give you an idea of, it's like looking in the mirror. But anyways, again, it's giving you a sense here. If you didn't have your graphing calculator, this is another way of getting some information from calculus. And for you, what's important is that it helps you visualize just all this hocus pocus you've been doing, right? You're talking about rates of change and how it affects these curves. Now you can see it happening, which is really the best reason to study the curve sketch. Okay, so you and a neighbor, this is a great way for you to recap. See if you can handle a curve sketch, x to the 4 minus 4x cubed plus 10. I'm just going to try to catch up. I realize that you're not finished yet, but you can bear with me as I do this on the board. Okay, so at this point I have all the background information that I'm going to need to make a sketch. I don't really see any other easy points to get. You're welcome to try, like, if you want to put in x equals 1, that's not very hard. I mean, that might, we'll just for good measure here. If I put in x equals 1, it's going to be 1 minus 4 plus 10. That's not too painful. So that's 7. You could put more points in here if you're worried about the shape, but I think that's enough for us to get going. I don't know why my projector does this with the resolution, but I'll have to put my couple missing lines in here. So the first thing I have is 0, 10. That's right there. Then I have 2, 6. So if that's 5, 6 is right about there. 3, sorry, -6, thank you. Should be right about there. And 3, -17. So here's 3. That's -15, so -17 is probably around there. And then I also said we could do 1, 7, so I might as well. 1, 7 will be right about there. So these dots don't mean a lot unless we know how to connect them properly. It says what's happening in this first spot over here, on this spot left of 0. What does the curve look like in our decreasing and concave up? Okay, so that means that if we want decreasing and concave up, it's actually getting cut off a little bit here. It would kind of go like this. Okay, and then the next region, what's happening? Still decreasing, and now, so I have to change the concavity. And remember, even though I put this dot in here, I'm actually going all the way to 2, because that's the next spot here for my interval. So I'm going to have to go decreasing and concave down. So it'll go like that. And then I have the next interval, which is decreasing but concave up. So it'll go like this. And then finally increasing and concave up, which should look like that. Okay, so I don't know how reasonable that is, but just to show you what's happening, we'll take a look on the graphing calculator. So x to the 4 minus 4x cubed plus 10. And I'll use a similar window. So my window goes from the minimum x value here looks like -1. And the maximum is what, 5? Yes. And the y minimum is -20. And the y maximum is 15. So hopefully this ends up looking similar in shape. Look at that, eh? Okay, so that's really as much curve sketching as we're going to need to handle. There are a couple tricks that you can do. I'm not going to get into any major depth of tricks, but what do you think about this one here? Well, we can do quotient rule and we can go through the way we did, but I'll leave it for you to give it a try. There's some strategies involved to it. As long as you've done your first derivative and second derivative properly, and you found your critical numbers and your inflection points, you're going to have the correct sketch. It just may be more convenient if you do a little strategy when you go there. So give that a try. I'll catch up to you. When I'm referring to strategy, of course, in this one, it's really about how you let the derivatives unfold. For example, the first one, we might as well just get started and see what comes out. So I've got, so the first derivative is 2x, x squared minus 9. And then I'm going to have the derivative of the bottom is 2x, and the top is x squared. So I don't know if you're getting used to this yet, but you really should try to factor as much as you can before you expand and collect. If you do that and take the 2x out, you'd have a 2x and x squared minus 9 minus x squared. Oh yes, thank you. So that means you end up with just a -9 on top because those are gone. So you'd have -18x over x squared minus 9 all squared. Okay, so that gives me some critical numbers. What do we find? 0, 3, and negative 3, yeah. So there's 3 critical numbers there. I'm also going to take a look at the second derivative. So the derivative of the top is going to be just negative 18, x squared minus 9 squared. Take away the derivative of the bottom. So the derivative of the bottom is going to be 2 times x squared minus 9 to the 1 times the derivative of the inside, which is x squared, and times the top, which is negative 18x. And we square this again, so now I have the fourth exponent when I have the bottom. Oh yes, it shouldn't be a x squared, it should be a 2x, thank you. Getting too excited here, I guess. So I'm going to try and take as much as I can out. So this piece here, I can take out, they all have a negative 18, and they all have an x squared minus 9. So that's what I'm going to try to factor out here before I do any collecting like terms or anything like that. I'll have negative 18 x squared minus 9. And then what I'm left with, this piece will only have 1 x squared minus 9. And then the other piece here, maybe I'll just do this for now, that negative 18 is gone, and this piece is gone as well. So that means I have minus 4x. 4x squared, yes, thank you. 4x squared. Because there's an extra x there, yes. Okay, so now's the time to collect up your like terms. X squared minus 9. And I'm going to have, let's see here. That'll be negative 3x squared minus 9. And I'm also going to factor out a negative 3 here. It's going to help me do my, when I factor looking for the inflection points. So that means if I take a negative 3 out, this negative 18 is going to become positive 54. And here it's going to become x squared plus 3. So there's no way for me to make this one here equal to 0. No way that it equals to 0. So it's not part of my consideration. The only place I'm looking for where it's going to be equal to 0 or undefined is at plus or minus 3. So the other points I'm looking for here are at x equals 3 and negative 3. So I've sort of run out of room there. I'll put them like this. I've got the derivative and the pieces that derivative has on it. Well, if you look at the pieces here, this bottom piece, it's not really going to change anything because it's squared. So I don't need to include it in a number line. It's going to be positive all the way across that number line. So you can, just means you'll do a little bit extra work when you figure that out. Up top, this negative 18x though, I do have to deal with that. So that's the only one that can affect this one here, is the negative 18x. And if I put in negative numbers, it's going to come out positive. If I put in positive numbers, it's going to come out negative. So that tells me about the first derivative, where it's increasing and decreasing. Now I'm going to look for its concavity. And in this case, it's 3 and negative 3 that make the switches, so it's going to be x plus 3 and x minus 3 that are going to give me changes to this second derivative. So I'll probably add an extra number line here just to make it go smoothly. So these two here are from the second derivative, and this is x plus 3, x minus 3. So it's negative, positive, 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 and negative to there and positive onwards. So overall, I end up with a positive, a negative, and a positive. And these make up, that's the first derivative sign right there. So, I mean, I guess it's not a bad idea. We've done all this work. Where's the extrema? Which point here could be considered a relative minimum or maximum? I only see one point that meets the definition for extrema. 0 is the one point where there is extrema. How come? Yeah, it continues to increase. So if you thought 3 was the biggest, the reason that can't be true is it's still increasing after that. So you get all the way up to 3 and you keep increasing. So for us, this is the only relative minimum or maximum. Which one is it, a minimum or maximum? It's a maximum because it's increasing, it hits 0, and it starts decreasing. That means it's got to be the biggest point there. Okay, what about inflection points? Where would you expect to find the inflection points? Yeah, negative 3 and positive 3, because the concavity changed from positive to negative, and here because it changed from negative to positive. Okay, so let's start our sketch then. I'm going to be looking at those 3 spots. F at 0, it's going to be a 0. There's the function in case you can't see. F at negative 3, it's going to be 9 over, let's see here, uh-oh. What does that mean? Good. That means there's an asymptote there. So it's not that the feature doesn't matter. It just means it's not a point or a place that we're going to find on this graph. That feature is an asymptote. So at negative 3, that's what we'll have here as a vertical asymptote. Okay. And then at positive 3, same problem, right? Dividing by 0, so there must be a vertical asymptote here. So that's the feature that we're going to plot. And we also have 0, 0 in this graph. Okay, so as I move along, let's see what happens here. Let's see, do you think, well, we've got increasing and concave up. So, like this? Hang on, I'm asking. It's not correct.
No.
Why do you think? What do you think I might have missed here? Well, what other key features might be on this graph? A horizontal asymptote might be on this graph, right? How do we find horizontal asymptotes again? With the graphing calculator, yeah. Do you remember how we do this? The Bill Gates math, right? Bill Gates has $1 billion, and you take away 9, and yeah, I know you guys all freaked out that I took $9 away from your billion, but in reality, it's not such a big deal. So really what we're going to be dealing with here is the limit as x goes to infinity of x squared over x squared. We're only interested in those most significant spots, so we're going to have 1. If I try the limit as x goes to negative infinity, which is the left side of my picture, because I'm squaring it, that means it's going to give me the same answer. Whatever negative number went in gets squared, becomes positive. It's also a 1. Okay. And if you're not confident at this point with the way the graph is going to look, then plot some more points. This is the bare minimum to help you sketch the curve. Anything extra is obviously going to be helpful if you need it. Yeah, and so now we can see this horizontal asymptote. It's concave up and increasing, so it should look like this. Then it goes to increasing and concave down. So here's what it would look like: increasing concave down, and it stops there. Then decreasing concave down. And finally, decreasing concave up. So decreasing, but concave up this time. Okay, so remember that when you're sketching the curve, we started talking just about the critical numbers and inflection points. The other thing you're going to need to look for today is vertical and horizontal asymptotes. Okay?